Hi guys. Yeah, let me switch the Google Meet. Yeah, window back to Gopher. Yeah, hi, good morning, Glady. So I'm amazed. At this point in the semester, you guys should be like exhausted, and it might be really hard to get up in the morning. Okay, so yeah, welcome to another episode of Polly's Introduction of Computer Networks. And good morning, Kevin. You know what? Let's check out the topics today. Today is actually quite important. Yesterday, we talked about the congestion control mechanism in TCP, right? Remember, there's AIND in the steady state that is called the congestion avoidance state. And then Polly introduces also steady state. Therefore, the opposite is like initial state or unstable state. Yeah, that state is called the slow start state as well. And the Windows control mechanism is not quite AIMD, it's EIMD. So it's a little bit more aggressive, increasing the window size. Instead of additively increasing, it's exponentially increasing it. Right. And so I think the last video yesterday talks about when do we know, right? TCP is supposed to drop the window size. That is by detecting a packet loss. Okay. In TCP, there are two ways, right? We detect there's a loss, therefore we need to retransmit the packet. One is more serious when timeout occurs, right? Because during a certain amount of time, there's no ACK coming back at all. The other is called the 3 duplicate ACKs, right? That's an optimization to TCP so that we could retransmit a little bit earlier. Okay, because receiving duplicate ACKs consecutively for multiple times means that, yeah, there's certainly a gap there, right? The sequence number before, or no, the sequence number right after the duplicate ACK. Okay, so duplicate ACK is in a way a call, a cry to the sender. Hey, send me this packet. I'm expecting this packet. You see? So we now know how TCP increase the window size, and there are two different ways depending on whether it's in the initial state or the steady state. And we know how TCP drop the window size. If it's the less serious case, we just drop it to half. If it's the more serious case, then we drop it all the way down to 1 and almost like restarting everything. Okay. Now, you might be thinking that why so conservative when we are dropping? Because the consequence of running into a congestion on internet is very costly. A lot of times you just drop a whole bunch of packets, okay, and then you start again, right? It's a waste of time. It's also a waste of what? Bandwidth. So on the internet, the dropping of the price is very aggressive. Unlike in quiz 26, right? Your guesses is actually somewhere in the middle, right? Much like the binary search. Increase can also be aggressive, okay? But on the internet, more conservative. But what's common between quiz 26 and TCP's congestion control is that you're guessing. TCP is also guessing. Okay. When it sounds like, oh, we have more space to send more packets, then increase the window size. Well, if we begin to see duplicate ACKs or timeout occur, lower the window size. All right, and today, you know what? The first video is still about TCP, and it is about this. Hey, didn't I mention that there's initial state and steady state, right? In initial state, you do increasing, decreasing this way. In steady state, differently. But how do you know? How do you know if a TCP connection is in the steady state, or in the steady state, or in the initial state? Yeah, there's a special parameter called SS thresh, slow start thresh, okay, for a TCP connection to determine whether it's currently in the slow start state or in the congestion avoidance state. So what I'm illustrating here is TCP Tahoe's window size changing over time. At the beginning, window size set to 1 segment. And then slow start, right? This is the initial phase. And therefore you see exponentially fast growth, the concave curve. And this is going to go until we hit the slow start threshold. That's when we exit slow start and enter congestion avoidance, where we do AIMD, so additive increase. At this point, we detect a packet loss due to 3 duplicate acts. But in Tahoe, we'll just drop the window size back down to 1 again. And then slow start again, a concave curve, until we hit the threshold again, and then AIMD again in the congestion avoidance state. Now, what's in Reno is, however, when we detect 3 duplicate acts, a packet loss, what we do is more simple, where we just reset the window size to half of the original window size, which is 12. So we set it to 6, and then continue to grow the window size AIMD, such as in the congestion avoidance state. Okay. Now, by looking at this plot, you also see, hey, we are switching from the slow start to the congestion avoidance state using the threshold. At the beginning, the SS thresh is initialized to a fixed value. But afterwards, you see the SS thresh is also changing. And when we detect a loss, when we need to reset the congestion window size down to some lower value, when that happens, when the packet loss is detected, the threshold here is also reset. And the value is set to exactly half of the window size before the packet loss is detected. So SS thresh is set to half of the window size just before the loss event. Okay. So in the TCP Reno's case, it's convenient. We set the threshold to the half of the window size, and we also set the window size to half of the earlier window size and continue to grow like this. So it's also saying passing the threshold and then this connection in the congestion avoidance state. If we go back to the original question asking, when do we switch from the slow start state to the congestion avoidance state, or from exponential increase back to linear increase? And so it's very clear. Once the congestion window hits the SS thresh, the slow start threshold. Because if you look at this, slow start, passing the thresh, growing linearly. Slow start, passing the threshold, growing linearly. And in this case, we see 3 duplicate acts, therefore we drop the window size to half, and we drop the SS thresh also to half. But hey, as long as it's beyond the thresh, the window size grows linearly, then the design does not conflict, okay, with other parts of TCP's congestion window adjustment mechanism. All right, now we can start introducing the finite state machine of TCP's congestion control mechanism. So in fact, we have already talked about TCP's congestion control mechanism. So in a way that I'm using the finite state machine as a summary to make everything concrete. So the first video here is to talk mainly on the slow start state. Now let's summarize TCP's congestion control. And what I'm going to show you is actually a little bit more formal using a finite state machine. And you see how TCP Center here implements, okay, the mechanism of adjusting the window size. The full finite state machine has 2 states, okay? Each represents, different phases of TCP's congestion control in a connection. So the first is the initial phase, the slow start phase. Initialization transition here is actually initializing the congestion window size to 1 segment, and then initializing the SS thresh to 64 kilobytes. I think this number could differ from operating system to operating system, and then initializing the duplicate act count. All right, so that was clear. Let's move to the normal transitions. There are 4 of them. Okay. If you look a bit closer, the top 2 here are actually the transitions handled in the cases where the sender receives acts. The bottom 2 are the cases where the sender detects losses. So this one here is actually detecting a loss due to receiving 3 duplicate acts. This transition here is actually detecting a loss due to timeout. Now let's talk about each of these transitions a bit more. So number 1 here is if we receive a new act. Now, according to slow start mechanism, the congestion window needs to be incremented by 1 segment, and that's it. So duplicate act count is reduced to 0 just so to clear all the duplicate egg counts because now we are receiving a new egg. So we should definitely clear the dupe egg count. And at this point, then we employ the rest of descenders mechanism, the RDT part of it, so that we what? Slide the window over and then send new segments. And how much we send out there depends on the result of the congestion control mechanism working. And next, transition number 2, this is when we receive a duplicate egg. So what we do here, of course, increment the counter for duplicate egg. And what do? The congestion control process, no more, right? Unless the count here reaches 3. That triggers transition 3. Okay. Now in RDT of TCP, this event is going to also trigger fast retransmission. So in a way, when there's dupe egg count equaling 3, then we do something for the congestion control and then some more for the reliable data transfer. Now in the congestion control, what we do is setting the SS thresh to half the window size, and window size to half of the current window size, which is now the value of SS thresh. And then reset the duplicate egg count, right? And then we can begin doing the RDT, which is to fast retransmit packets. Now the number of packets we can send now then is determined by the condition window size we just set aside earlier. Transition 4, this is also packet loss, but this is packet loss detected by having a timeout. So in this case, the congestion control says we need to set SS thresh to half of the window size, and the window size all the way down to 1 packet, and then reset the dupe egg count. And then from here, the RDT mechanism, which is what? To retransmit the missing segment. And because this time, in this case, congestion window is set to 1 packet, therefore we only retransmit 1 segment. Okay. No matter how it is, how many packets have been sent, how many yellow packets or yellow bytes are there in the sliding window. All right, so next, the congestion avoidance state in the finite state machine. Done with the slow start state. Now, let's move to the congestion avoidance state. So the first thing is, hey, when do we transition from SS to CA? Yep, when the congestion window size is larger than the SS thresh. And that takes us to the congestion avoidance state, where we see again, transition new egg, transition duplicate egg, transition dupe egg count equal 3. And hey, where's the timeout state? Well, the timeout state is actually here, right? Because when we're in the congestion avoidance state, timeout is actually series packet loss. We reset the congestion window down to 1 end. Start from the slow start, increment the window size exponentially, start from the slow start. So we need to do a state change in this finite state machine, going back from CA to SS. Okay. And otherwise, all these the same, just like timeout event. Similarly, for dupe egg count equaling 3, all the same, Okay. Actually, similarly for dupe egg, just incrementing the duplicate egg count. But the last one, the new egg, wow, we need to be careful here, all right? Because in SS versus CA, when we receive a new egg, meaning no loss, we actually increase the window size differently. So yes, this is what you see here. In SS in slow start, we're incrementing the window size by 1 segment per egg. Here, we need to increase the window size by 1 segment per round trip time. So be very, very careful here. This is receiving an egg, not, hey, checking and we see that there's 1 round trip time elapsed. So we need to figure out exactly the amount to increment to the window size so that after 1 round trip time, the increment will be exactly 1. And how do we do that? Think this. If the window size is CWND and the packet size is MSS, how many packets will be out in 1 round trip time? This many, isn't it? Okay. And after all these packets come back in, the increment of the congestion window should be 1. That is saying we cannot be incrementing the window size by MSS. We need to increase this much. Okay. After this amount of packets received, then we add to this value. So we need to divide this value by these. That would say this is the amount we need to increment per packet. Okay. So if we rewrite this formula here, it's what? MSS multiply, so MSS multiply reverse of CWND to MSS. So after reversing, MSS at the top and then CWND at the bottom. And that is TCP conditions control sender's finite state machine in a simplistic way. You see here, let me summarize again. Yeah, so these are the events receiving new ACK. These are the events handling timeout. And these are the events handling receiving the duplicate ACKs and it's reaching the count of 3. All right, so that was essentially the finite state machine of TCP's condition control. Okay, so essentially what you hear is that in the slow start state, the increase of the condition window size is EIMD, but in condition avoidance states, it's AIMD. All right, and there's a threshold determining whether we switch from the slow start state to the condition avoidance state. So quiz 27 is asking this. Consider this scenario on the right. Host A is the data sender. Host B is the receiver. Okay, so the guy sending the ACKs. And let's suppose that at this point in the transmission, in the connection, the congestion window size is 5 MSS. The threshold is A. And so given that the congestion window size is 5 MSS, so what is MSS? Maximum segment size. That is saying that the largest size, the largest number of bytes you can have in a packet. So usually TCP implementation typically send as many bytes as possible in a packet because that's the most cost-effective way of generating packet. Because I think if you recall, right, the header of TCP packet is 20 bytes already. If you send a very small data payload, small packet with only 20 bytes, then the overhead is 50%. Okay, so you send as many data bytes as possible. And what is the maximum data size? MSS. So this is saying that if we send the data in the most cost-effective way, we'll be sending 5 packets here with the window size 5 MSS. Okay, so 5 maximum packet size. And therefore these 5 packets will be carrying sequence number what? 0 MSS, 1 MSS, 2 MSS, 3 and 4 MSS. So each packet is 1 MSS large. All right. So these 5 packets will go out. The first 3 will arrive fine. The 4th will be lost. And the 5th arrive at the receiver. Okay. You see that these 3 first data packets will be detected by host B as, oh, good, expected data. Therefore, the acknowledgement will be sent, okay, accordingly. First acknowledgement will be what? Expecting the next packet being sequence 1 MSS, so ACK 1 MSS. Second one arrived, expecting next 2 MSS. Third, 3 MSS. The 4th is lost. Therefore, the 5th packet here arriving, B will see that this is not as expected. There's a gap. Therefore, it sends the ACK previously generated. Okay, and guys, if you recall, at the very end of TCP's RDT, Poly introduced this thing called delay ACK receiver. Okay, so in this scenario, this is a non-delay ACK receiver. For every packet, you send an ACK. All right. All right. So hey, back in host A. Host A receiving ACK 1 MSS. Hey, according to the condition control mechanism, right? The condition window size when we receive a new ACK, it needs to be updated. So, what is the value of B after receiving ACK 1 MS? And what is the value of C, D, and E after receiving 2, 3 MSS ACKs? Okay. And so tell Poly B, C, D, E when A equals 7 MSS. So A here, if it's 7 MSSs, what is the state of the connection right now at the beginning, right here? Yeah, it should be so star, right? But in case of Q2, A equals 5 MSS. Ooh, if this is the case, we'll be in congestion avoidance state. Okay. Yeah, I think you get the idea of quiz 27. Essentially, you need to calculate the congestion window size after receiving X when you are in the slow start state versus congestion avoidance state. Oh, and pay attention. Sometimes you might start from the slow start state, but as the window size increases to a point that it arrives at the threshold, then you might move in the middle of receiving X to the congestion avoidance state. All right, good. So quiz 27, it's actually a little bit more challenging from previous semester's quiz 27, but no worries, you will be given a little bit longer time, okay, so that you can think this through. So now let's go to week 11, quiz 27. You guys would have 6 minutes time to work on this quiz, okay, and Polly start counting now. Let's go. Yeah, I see you guys started thinking, started calculating. The actual CWND is by count as well. Okay, and in the quiz here, we're using MSS as a unit, and MSS is actually a value that's pretty large. So of course it can be a fraction of MSS. All right, so yeah, there are several teams who managed to come up with their answers. Okay, let's check these out. Okay, so Walker is saying that 6, 7, 7 and 1/7, 7 and 1/7. Okay, so the duplicate act does not increment the window size for sure. So this is definitely okay. And at the beginning, we are in the slow start state. Yeah, so 5 incremented to 6 according to the finite state machine, right? But when the window size reaches 7, that's the initial threshold, right? Then we'll be entering the condition avoidance state. Okay. For each egg, what we increment one window size, okay, of a packet, of a window size. Okay, it's a little bit hard to say, okay, because the window size is 7 packets. Then we increment only 1/7 of a packet. The idea is so that after 7 packets, the increment of the window size is about 1 packet. And therefore for Q2, 5 plus 1, 5, 1, 5, and 5 plus 2/5, 5 plus 3/5, okay, and then duplicate X stay the same. You know what? This is definitely falling in the ballpark, although it's not exactly following the equation. Right? So that Polly take you guys through Polly's calculation. Okay, that way you might be a little bit more comfortable. Okay, so here for Q1, that means A equals 7 MSS. So receiving this first egg, B equals, according to the equation here in slow start state, condition window size plus MSS. And condition window size is 5 MSS. Therefore, we end up with 6. Similarly for C, condition window size plus 1 MSS, 7. But at this point, we enter the condition avoidance state, don't we? Therefore, D here, yeah, we are receiving a new egg, but then we trigger these events, and this is what? Incrementing the condition window size differently from in this state, receiving new egg. And this is the formula. Condition window size is 7 MSS, and this is what? 1/7 of an MSS. Okay, and E is trivial because it's a duplicate egg, so we stay at this condition window size. All right. And so some of you ask about whether the condition window size can be a fraction. Yes, it can definitely be. The actual condition window size is counting by bytes. And for simplicity, I use MSS here as a unit. That is 1 maximum packet size. And you know what? The reason that I do it this way is because in typical TCP implementations, if there are more data to send, you would try to send in the maximum packet size, 1 MSS as possible, instead of chopping it into smaller packets. All right. So when you have such a window size, 7 and 1/7 MSS, what do you do next? Okay, when you receive this first egg, this incremented to 5, so you can send 2 more packets, right? But you see here, you can send definitely 2 more packets, but there's 1/7 remaining. Yeah, you can actually send 2 packets. The first one is 1 MSS, and the second one, 1/7 of an MSS. Okay, so you see that the rule, okay, in a typical TCP implementation is that if you have partial MSS bytes in remaining condition window, you generate a packet with partial MSS. Okay. Now, Q2. Okay, so this is the case that's a little bit more interesting. We are in condition avoidance all the way. Okay, so first B is triggering new egg here, and therefore we follow this formula, and it's 5 MSS, the initial window, the window size previously, and this is 1/5. Okay, because we have 5 MSS. Okay, MS divided by 5 MSS, that's 1/5, and that's 1/5 of an MSS. And so if you develop the formula, develop the terms, and then you come to 5.2. Okay, and I see that some of you say 5 plus 1/5. Some of you say 5.2. What about C? So This is just so that you know, to be exact, 5.2 here, or 26 of fifths here is the exact window size. And this is the reverse of the window size. Okay. I have to say, yeah, after adding all the numbers together, it's very close to 5.4. Similarly for D, okay, 5.39 here and 1 over 5.39 here. The sum is very close to 5.6. Okay, so this is, you see that generally, if the window size is 5, then it takes 5x to increment the window size by 1 packet, 1 MSS. Okay, good. So this is quiz 27. I hope it's clear. And you know what? The next topic is still the congestion control of TCP. There's an optimization for TCP's congestion control. It's called fast recovery. Okay, I know you might still be struggling with quiz 27 a little bit, but I think if you get the rough idea, it's okay. Okay, pay attention to this video because this optimization is actually implemented in TCP, unlike delay ACK. Okay, so this finite state machine, now we walk through it. It's kind of symmetric and clean, relatively easy to track. This is also the mechanism implemented in the TCP Tahoe, the version 1. In TCP Reno, it's actually being extended. So the hack here is called the fast recovery. Okay. Now, this version looks substantially complicated, but let me tell you this, hopefully makes it a bit simpler for you. The only transitions that are actually touched from the previous finite state machine are just these. Okay, the case where the dupe at count reaches 3. So previously what we do is this. We set the SS thresh to have the window size and the window size to SS thresh. But now, okay, in Reno, we actually add 3 more segments to the window size. So we are actually a little bit more generous about setting the window size. And the logic behind this is, if we receive 3 duplicate acts, that means the channel between the sender and receiver, there's enough capacity to allow 3 data segments to go. Although out of order, still triggering duplicate acts to come back, right? So 3 spaces, therefore generating 3 duplicate acts. So there's enough capacity, right? So we don't have to go all the way down, or half down. So as long as, hey, we're seeing, duplicate acts, that means the capacity is still there. Maybe this is just a very, short-term congestion, short-term pre-congestion, okay, happening. So maybe we just keep, pushing a little bit more, and when this short-term outage or short-term congestion goes out, then we can come back to normal. Okay, so this is the logic behind the fast recovery mechanism here. So after adding 3 more segments to the window size, we enter the fast recovery state. And staying in the fast recovery state, we apply the same logic. As long as we receive a duplicate act, we continue to increment the window size. Because being able to receive a duplicate act is because we allow 1 data to go out, right? Yeah. So this is going to be repeated until what? Until we finally get a new act back, or all these extra packets we send out by being more generous about the window size somehow get dropped in the middle, meaning the congestion is not short-term. It's a bit more pathological, persistent. So we will run into timeout here. In this case, drop the window size to 1, feel free. But if it's in this case, it's okay. Then we can just reset the window size to normal, which is half of the window size, and then go back to the congestion avoidance states, and then begin linear increase again. All right, so that is fast recovery. Okay, so when we receive duplicate acts, okay, and enough of these duplicate acts, we will actually enter this fast recovery state. And in the state that for every duplicate act, we keep incrementing the window size so that we keep sending data and see how bad the condition is. Okay, it's a little bit counterintuitive, but also intuitive. Okay, that is the nature of fast recovery. I'm actually not quite sure that you get it or not, but that's exercise, okay, through quiz 28. So you see here the finite state machine of TCP with fast recovery. Okay. And the scenario on the right is very similar to quiz 27, right? We send 5 packets because the window size is exactly 5 maximum packet size. And threshold, oh, this time higher, 10 MSS. Okay, and we also drop the 4th packet. Okay, and there'll be 4 eggs coming back, and they will trigger the condition window size to change. Now in this scenario, it's always below the SS thresh, so 5, 6, 7. Until the 4th egg, it's a duplicate egg, so condition window size stay at 7. The thing is that after the condition window size is increased to 5, here, host A, because receiving a packet, we open up one window, open up one MSS to send the next packet, but also the window size is incremented by 1, so that's 1 more packet we can send. So we send 2 packets, okay, receiving the 1st egg. Similarly, 2 packets receiving the 2nd egg. And these eggs will carry sequence number 5 MSS, 6 MSS, 7 MSS, and 8 MSS. And these eggs coming to host B will generate what? More duplicate eggs, don't they? Yeah. So this is first egg 3 MSS. This one will be the first duplicate MSS. You know what? These 2 will be what? Generating also duplicate eggs, and this will be the 2nd duplicate. This will be the 3rd duplicate. Okay, they are all duplicates. Therefore, the duplicate egg will be just counting. Okay, until when? Yeah. And then, hey, follow the finite state machine and tell me. Okay, receiving the 3rd duplicate egg, what is the new threshold and what is the new condition window size? Okay. Similarly, if we keep receiving duplicate eggs after the 3rd duplicate eggs, so you see packets 7 and 8 will also generate duplicate eggs, right? 1 more duplicate egg, 2 more duplicate eggs. What will be the threshold and the condition window size accordingly? And more. After receiving the 1st duplicate, 2nd duplicate, 3rd duplicate, the window size might be changed, right? And if it does, what is the packet being sent next? Okay, what will be the value of C? And you know what? Receiving more duplicate X means that there might be more packets. Okay, the sender can generate. Because, you know, as we receive more duplicate X in fast recovery mode, condition window size keep increasing. So, if there are more packets being sent, okay, after receiving the 4th duplicate X and the 5th duplicate X, what will be the packet sequence numbers, okay, being generated? So that is quiz 28. Derive the value of A, B, C, D, E, F, G, H, I. Okay, so this one is really tough. And by the way, the assumption is that there are always data from the above. Okay, there will be always data that the sender needs to send. Okay, therefore send the data in MSS if possible, unless it's restricted by the CWND. Now, if there's partial MSS in the remaining CWND, then you generate a packet with the partial packet size. All right? So be careful about what H and I might be. Okay. C might still be a little bit straightforward, but H and I might be a little bit interesting. Okay. And you know what? I say C being generated, but if the window size shows that there's some partial thing into it, or more than one packet can be generated, C here tell me multiple numbers. Okay, if there are 3 packets being generated there by receiving the 3rd duplicate X, tell me 3 numbers in C. Okay, good. So substantially harder. Let's move to Discord channel W11 quiz 28, and you guys have let's see, 15 minutes. Okay, that's crossing over through the entire break. So essentially what I'm gonna do is this. I pronounce that we will start breaking now, and you work on quiz 28, and we'll return at 11:20. Okay, so we'll return at 11:20, and we'll check out you guys' solution for quiz 28. All right, good. And break time. All right. I see that this quiz is probably too challenging. Yeah, so that Polly work it out and see if you find that you are agreeing with Polly. Okay, so sorry, these should be 6, 7, and 8. Okay, obviously it was 5 originally, and receiving a new egg, yeah, incrementing it to 6 as it's still in the slow start state. Okay, so this is no problem, 6, 7, 8. Now, Polly did not draw these 2 additional packets being generated by the egg equal 3MSS because it's already very crowded. Okay, but you're right, there should be 2 more packets here, and that should be 9 and 10 MSS. Okay, so now, hey, what should be the value of A and B? This is egg 3MSS, and this is the first duplicate egg. This is the second, this is the third. Okay, what do we do when we have 3 duplicate eggs? Okay, 3 duplicate eggs in slow start. Okay, well, we do this. They are the same. Okay, so they look the same. They are the same. So essentially, change the threshold to half the condition window size. Wait, it's not showing on the whiteboard. So I'm talking, but you're not seeing. Oh, okay, it's showing. Good, very good. Okay, yeah, it did. Okay, showing on the whiteboard. So SSH should be 1/2 the condition window size, which is A right now, right? So at this point, 4. And the condition window size is what? 4 plus 3, according to this. SS thresh plus 3. Therefore, 7. Let's see, Oscar here from team 7. Okay, A equal 4, B equal 7. Very good. So let me come back to the derivation. Okay, so 4 here, 7 here. Okay, so far so good. Now, what about the fourth egg? So we are already in the fast recovery state, right? Because this transition will trigger us to the fast recovery state. And if we receive duplicate egg again, what do? Oh, we increment the condition window size by 1 MSS. So this was 4 and this was 7. Well, we did not change the threshold, so this remained 4. And the condition window size will be incremented by 1, 8. Yet another egg, duplicate egg, so we're still in the fast recovery state. So apply the same equation again, 4 and 9, right? So hey, guys, you guys are pretty good. Team 10 here, as well as I think previously Oscar was team 7. Yeah, 4, 7, 4, 8, 4, 9 for the window size, no problem. Okay, 4, 7, 4, 8, 4, 9 for the window size, no problem. Okay, now what about the packets that we might be generating, okay, in the fast recovery state? All right, so let me clear the markups. Okay, so we know this is 4, 7. This is 4, 8. Can we send packet out here after the third duplicate egg? Can we? It depends on how many packets are out already, right? Condition window size is 7 packets. How many are already outstanding, waiting for eggs? You know what? 3, 4, 5, 6, 7, 8, and 9, 10. They are all waiting. So there are 8 packets waiting. The window size is only 7. So what should be C here? Yeah, sorry, we cannot send any packet here. What about here? H. At this point, window size is A outstanding packet. There's no spare bytes to send. So this is still an A. But this guy, third, fourth, the fifth duplicate ACK. Window size is now 49. Can we send something now? Yes, we can. And the Windows, the sequence number will be 11. Okay. Very good. Okay. Yeah, I know it's a little bit tricky. Yeah, NA or null. So if we come back to the Discord. Let's see. Okay. Yeah. Oscar, CHI. Yeah, reconsider it. Okay, CHI, reconsider it. But I can understand. After 3 duplicate ACK, according to TCP's RDT mechanism, right? You retransmit a packet. Yeah. So I guess Oscar, your solution will also be accepted. Okay. Yeah, I know Jin Yang also corrected according to what I was describing, but this C equal 3, yeah, will also be accepted. Okay, although the window size does not allow, but we do have fast retransmission mechanism. If that option is on, yes, we'll need to retransmit packet 3. So you guys, 7 and 10 was also right. Okay, but H, right, the sequence number, yeah, so this is definitely an A. Okay, so this is definitely an A. All right, good. So accept it. NA, upon receiving the third duplicate ACK, this is the no fast retransmission option. Okay, so I was not clear about whether we implement fast retransmission here. Okay, so for Oscar, Team 7, this is accepted, but still H will not be sending 3 packets. All right, because the window size is 9. Oh, actually no, window size is 8. Okay, so no packet sent there, but 11 sent here. Great. Yeah, so you guys are getting it. Very good. All right, so fast recovery. You see that it's a little bit trickier. It's a little bit trickier, but you can probably see the benefit of doing fast recovery. So you still push to send more packets. Yeah, good question, David. In case there's no fast retransmission option turned on, yeah, it will be, in case there's timeout, then it will be retransmitted after timeout. You know what? You know what, David? I think you are asking a key question. Guys, fast retransmission option must be on. So I think Oscar here and Jin Yang's initial solutions are better, are actually correct. We must send 3. Because the whole purpose of doing fast recovery is so that we could trigger 3 duplicate ACK retransmission better. Yeah. But you know what? I will accept either. Okay. So 3MS will be retransmitted after timeout. So 3MSS, you know what? This is a very good question, David. I think 3 must be sent here. Okay. because it doesn't make sense. Fast recovery is to serve, okay, fast retransmission, because that way we get to send more packets, even though it generates duplicate acts coming back, but the sender gets an opportunity to resend. Okay, so, hey, sorry, poly needs to correct. My apologies. C needs to be 3. Okay, even though the condition window size is not allowing extra packet being sent. So I guess the reason that I'm debating is because there are 2 options. So one is to send one is to send packet 3 no matter what, regardless of the window size. Okay, the other is to send packet 3 here. Once we have one available window size, we retransmit. So in a way, after receiving 3 duplicate acts, we will be generating regenerating packet 3 or waiting to send packet 3. Okay, and once there's a spare slot, we send packet 3. Okay, so I think that is better. Okay. Guys, so in a way, Poly is collectively working with you guys to find the best answer for this. What's making more sense? Window size A, B, D, E, and F, G, no problem. I think C is still an A, H, an A, and I, you know what? Packet 3. That makes a lot better sense. So in case there's a spare window space, we send packet 3, the retransmitted packet. The third act should be triggering the sender pending packet 3 being retransmitted. Let's see. Oh, exactly. Retransmit missing segment. So I guess, yeah, you're right, Brian. You're right. Yeah. So C should be 3, no matter what, regardless of the window size. But in that case, I should be NA. Am I right? Yeah, I think I should be NA. So guys, once again, C should be 3, H, NA, and I, NA. David, Brian, I think you guys are getting it. Do you agree? Yeah, so many of you are misled by what Polly said earlier. Sorry about that. What do you think? You know what? I think I am probably right this time. I think I'm probably right this time. Okay, C equals 3, but H and I both NA. Because in the duplicate act equals 3 transition, once we change the window size and threshold, we immediately retransmit the missing segment regardless of the window size. But you see that there are still 9 outstanding packets there waiting to be acknowledged. Okay, so when we receive H and I, window size gets incremented to 9, but we cannot send more packet yet. Okay, so the duplicate act transition there says transmit only when the window size is allowed. And unlike here, just retransmit, force retransmit, not considering the condition window size. Okay, so let me correct and make sure that this time is making sense. So I think the window size part is okay. But when we receive the third duplicate act here, change threshold, condition window size, Of course, we changed the window size to, I think, 47 here. But we also do what? Here. Send the missing packet. Therefore, this C here must be 3. Okay, the missing packet here. Okay, C equals 3. Oops, sorry. This is not what I meant to do. C equals 3. And window size gets incremented to A, incremented to 9. But as we retransmit 3, we have outstanding packets. How many of them? Oh, no, we have 8 outstanding packets. You guys are right. You guys are right. Okay. So still, yeah, 3 to 10. 3, 4, 5, 6, 7, 8, 9, 10. Still 8. So yeah, we can still I equal 11. Okay. This equal an A. There we go. Doris, you're right. So A packets waiting. Yes, we can send one more packet. Brian, very good. Tricky. Yeah, so as I said, this one is the hardest. I think this time we are finally right. Okay, Polly is actually comfortable now. 3 for C. Oh, sorry about that. Three equals C, and then the H and A, and then I 11. This is 3, and this is an A, and finally I 11. Okay. All right, so that's fast recovery. Okay, a little bit tricky. But you know what? As we try to work through exercise quiz 20A, now everything is clear, including Polly. Okay, including being clear for Polly. Good, so let's move on to the next topic. These two topics are more research oriented. One is to try to model the throughput of TCP. Okay, so let's hear out this video. Somebody tries to estimate or calculate the average sending rate of a TCP connection. You see that the current sending rate is window size divided by the round trip time. But you see the window size increase, decrease, increase, decrease in a connection. So how do you calculate the average sending rate in a connection? That is what this video is about. Let's cover 2 more topics related to TCP, and these are about what the research community is doing trying to improve TCP for the future need. First is about how one improves TCP such that it can support long, fat pipe. Okay, what I meant by long pipe is a TCP connection that has long round trip time, and a fat pipe is that it has high throughput. Okay, and this is what we know. Okay, sending rate or the throughput should equal the window size divided by round trip time. So this is 0.1 second, and the rate should be 10 gigabits per second. So you see the congestion window is essentially the 2 terms multiply, and that is 1 gigabits and approximately 110 megabyte. So at the sender side, receiver side, 100 megabyte is required to buffer the packets that are in flight. And this is just to maintain 1 connection, right? If you have 10 connections, that's already 1 gigabyte of memory. If you have 100 connections, that's gonna probably take all your memory away. This is just one issue. Another issue is this. TCP is actually go back and like. What if you run into a packet loss that is triggered by having 3 duplicate acts? What we do there is we set the window size to half of the window size before a loss event is detected. And you know what? The window size, the number of packets there could be, can be as high as this, because if we divide this by 1500 byte, you get these many packets in flight. So in that case, we'll have to retransmit all the unact packets, okay, and half of the window size here. Okay, so that's, wow, 41 and 666 something packets that we need to send. And the bandwidth consumption there, right? The amount of bandwidth we might be wasting there is very significant. So TCP, the current design, isn't really ideal to support long fat pipes. And this is actually assuming that there's no packet loss at all, no bit error at all. What if we have error? One will have to derive the TCP throughput model considering loss before one can see how big a problem it is to try to support long fat pipes. So let's try to do some derivation here and see if we can come up with the average TCP throughput, okay, provided the window size, round trip time. The assumption is that let's ignore the slow start, okay? Consider just the condition avoidance operation and assume that there's always data coming in. And the scenario is very simplistic, which is illustrated here. Over time, the changes of the window size is exactly from half of W increase all the way to W, and W is where the loss will always occur, and therefore we drop the window size back down to half W because this is in condition avoidance. When there's a loss, drop to half W. When there's a loss at W, drop to half W. Okay. And so it's not hard for you to see what is the average window size? Yeah, the midpoint here, right? So 3/4 of W. And therefore the throughput is what? The average window size divided by the round trip time, which is this term here. Now, if we plug in, yeah, this is the goal throughput, and this is the round trip delay. Now, what is the window size now? Well, it will be this term multiplying each other and multiplying the reverse of 3/4. Therefore, it's 4/3 now. So this is actually even bigger than the CWND we're calculating there. So with loss, yeah, the amount of memory required to store data higher, the amount of unnecessary retransmission also higher. We can go on and on, right? Try to derive a more general model. So let me not go over the exact derivation, just tell you, if the loss probability is L, okay, one can actually come up with the TCP throughput being represented this way. Round trip time here, okay, square root of L here, and the maximum segment size here. Okay. Now, if take the same example here, take the same setting there. Packet size being 1500 bytes, round trip time being 100 milliseconds, and the goal throughput 10 gigabits per second. In order to achieve so, the loss rate needs to be as slow as this. 2 multiply 10 to the power of -10. Okay? Now this is a loss rate that's also impossible pretty much on the internet today. All right? So definitely we need new versions of TCP to support very high fat pipes going a long way. Yeah, so you see that it's actually surprisingly easy to derive the average throughput. Okay, and with a little bit more of a derivation, you can actually estimate what the throughput is going to be like given the packet loss rate. And so in order to generate very high throughput TCP connection, one will need to control the loss rate to be really, really low. Okay, and that is not easy to do. Okay, so that's what some of the research people are trying to do. Okay. Next issue regarding TCP is fairness. Why do we need to be fair? Well, actually, it's a philosophical question. So there are so many TCP connections around the world. Okay, should each of us get a fair cut? Okay, if the TCP connection gets throughputs that are not fair, I guess it's a little bit more controversial. Then somehow we try to keep it fair, isn't it? And so you see that TCP's AIMD mechanism, for some reason, okay, make sure the two TCP connections will approach a fair share of available bandwidth. Okay, here's the video telling why. Another major issue is this, fairness. Okay, let's talk about fairness at this level first, the TCP fairness. Okay, so what we're talking about here, the goal is to make sure that the K TCP sessions will share the same amount of bandwidth if it go across the same link of bandwidth R. So the eventual share of the sending rate or the throughput should be R divided by K. Okay, so in this scenario, what you're seeing is the router in the middle, the capacity is R, and we have two connections. So connection 1 here should have half of R, and connection 2 here should have the equal amount. So we have two competing TCP sessions, and they're competing for a link with capacity R. So what I'm showing here are the relationship of connection 1 and connection 2's throughput. So one extreme is connection 1 gets the whole R, while connection 2 gets nothing. And this is the other extreme. Connection 2 gets R, while connection 1 gets nothing. The fair point is right here in the middle. Okay, each of them gets half of R. So you see here, the dotted black line is to draw the equal bandwidth share, meaning if the bandwidth of connection 1 and 2 falls on this black line, yeah, they'll be fair to each other. Now, the blue line here, okay, is actually illustrating, this is actually the boundary, the capacity of the link. Okay? If the sum of connection 1 and 2 throughput goes beyond the blue line, that means congestion is beginning to occur, packets will begin to drop. Now let's say we start from here. Connection 1 having this much throughput, while connection 2 have very small throughput. As time goes by, okay, we're in congestion avoidance state, so we will continue to do additive increase. Therefore, connection 1's throughput will continue to increase, just like connection 2's throughput will continue to increase. And the characteristic, the value of connection 1 and 2's throughput will fall along this line here with the slope of 1. Now, as it goes beyond the blue line here, this is actually beyond the network capacity, we'll begin to see packet drop. And what we'll see next is what? The two of them reducing the throughput to half of the value here. Okay, so this is connection 2's. Connection 2's throughput drop to half of it. Okay, right down here. Connection 1's throughput drop to half of it, right down here. Okay. So having a loss, decrease the window size by a factor of 2, and that takes us from here down to here. So this is the current throughput of connection 1 and connection 2. Let's move on, right? It will continue to go additive increase as we are in the congestion avoidance state. Crossing the boundary of blue line, drop packet again, and decrease the window size again. Okay, again by factor of 2. So we go down here. So you see, additive increase, multiplicative decrease, additive increase. You see, the throughput of connection 1 and 2 are actually what? Approaching the equal bandwidth share. So TCP between the connections, the mechanism warrants that they will be fair to each other. So we see between TCP connections, they'll be fair to each other. But what about TCP to UDP? Multimedia applications actually prefer not to use TCP because TCP has this window size mechanism when there's congestion drop it, right? So the rate, sending rate is actually throttled by the congestion control mechanism. So some of the multimedia applications will prefer UDP, and they will send audio video data at high rate, constant rate without really adapting to congestion. So would that be fair? Of course not. And not to mention this, what if you have applications who open up multiple parallel TCP connections, okay, versus other applications who opens one TCP connection at a time to send data? Now consider this case. A link of rate R with 9 existing connections already, right? Then each have R over 9 share of the bandwidth. When there's a new app coming in asking for 1 TCP, that app then will share with 9 existing connections and each get 1/10 of the R. But if the new app comes in and then asks for 9 parallel TCP connections, so that will be what? R dividing by 9 plus 9. And each connection is this much because the new app gets 9 of these, so let's multiply this by 9. New app gets half of R. So a new app designing this way versus a new app designing this way, okay, competing with other existing connections, it's actually hard to make it fair. And you know what? Web browsers these days do this. Okay? They might start parallel connections to fetch one page. Previously, Internet Explorer were very aggressive. Okay, for example, starting 8 parallel connections, 4 parallel connections to try to fetch web objects in a page. But nowadays, the HTTP consortium actually regulates so that they do not overdo this. Yeah. So fairness, again, as I said, it's philosophical. Definitely, there are several internet engineers, very senior ones, think that it's better to make it fair. And as you see Polly illustrating that AIMD will actually take 2 connections throughput to equal share. But you also see from the video that one can always do something at a higher level, at the application level, such that you get an unfair share of throughput for your data. But anyhow, quiz 29 here is to ask you, maybe there's really benefit of doing AIMD, even though it looks conservative, because we see that the both connections transmission rate will converge to the equal share. Okay. So this question is asking, okay, would the 2 connections bandwidth share will be equal if it's not AIMD? If it's AIAD instead, will we achieve equal share? Yes or no? If it's MIMD, so there are 3 other combinations. MIAD. For these 3 other combinations of adjusting the window size, would we get equal share for connection 1 and 2? Okay, that is quiz 29. So let me invite you to channel W11, quiz 29. For this quiz, you guys have 4 minutes. Okay, and let's go. Okay, so I can see team 7, 8, and 1 all say no, no, no. Team 10, always on the same line. Same, always on the same line. Even more, yes. It would kind of diverge more, and it won't actually control congestion at all. Good. No, no, no. Yeah. So I think, so if we try to show AIADs, let's suppose that we start here. Okay, so this is connection 1. Oopsie, not straight at all. Connection 1's bandwidth. Connection 2's bandwidth. So connection 1 bandwidth is this much. Connection 2, this much. Okay, so AIAD means incremental, linear increase. AD, drop down back here. Not getting closer to this equal shared line, definitely. MIMD, the curve is a little bit tricky. If we start here, because we will double bandwidth here and double bandwidth here, so it will grow a little bit more like this, or maybe this. Because next time, I think it's still linear, right? And MD, it's just that the range of changing, okay, slightly bigger. Okay, so MIMD, it's not a oopsie. It's not a slope 1, okay, curve. It's actually depending on the proportion of connection 1's sending rate to connection 2's. But it's still a straight line. Okay. And MIAD, okay, so that is like increasing this fast and decreasing only this slow. Okay, increasing this fast and decreasing this slow. Yeah. So decreasing, I think it'll be very interesting to show it. Okay. So multiplicative increase will be incrementing twice, so a slower slope, but we'll be decreasing it. Sorry, yeah, not very good at drawing the proportions. Additive decrease and a slope 1 decrease, right? Go like this. Okay, a little bit weird, tilted sawtooth. So, but bottom line, none of these will get us the equal bandwidth share. Okay, sorry, equal bandwidth share. Okay, so this one definitely easier than quiz 28. Good. And next topic, in fact, the next topic is the last topic in chapter 3. Okay, the last thing we need to talk about TCP. And this is regarding this thing. We talked about 2 approaches to do congestion control. There is what? End-to-end, and there is also network assisted. Okay, so TCP, there's a certain option you can turn on called the ECN bits that would allow TCP to do something like network assisted congestion control. That was TCP, taking the end-to-end approach. Let me introduce another mechanism that's called the ECN. It's also defined for TCP/IP for the internet, but it's not really implemented or activated. And it's taking the opposite approach, the network-assisted approach. The ECN mechanism works this way. First of all, in the IP packet header, okay, or network layer header, there's this special field called TOS that stands for type of service. So in that field, 2 of the bits are assigned for the purpose. They are also called the ECN bits. Okay, so I'm using a green packet here to indicate that that packet header, especially the network layer header, is carrying the ECN bits. They were initialized to 0, that means no congestion, but as the packet travels through the network, running into a busy router like this, the bits will be turned on. And the packet will eventually come, okay, and arrive at the receiver of the data. And the network layer here at the receiver is going to see, oh, these 2 bits are turned on, therefore notifying the transport layer. point, okay, the transport layer of the receiver is going to do this. Receiver is going to send the ECE bit on the packet going back to the data source, like this. Okay, so it's going to be in the ACK packet and the ECE bit being turned on. So this is also called the E flag, okay, in the TCP packet field. Sender there, upon receiving this ECE bit packet, will then send a packet that is then the data packet going back to the receiver. And that packet is a little bit special because there's also a special bit being turned on, the CWR bit. So this is congestion window reduced bit. This is so that the destination here, the receiver of the data here knows that, okay, so my notification here, you indeed received it and reduced the sending rate. Okay, so therefore the receiver of the data does not need to send ECE bit again. Okay, otherwise, the source is going to reduce sending rate again and again. Right? And the E bit and the C bit, the E flag and the C flag are in fact again in the TCP packet header. Okay, so along with all these other flags for TCP. And that finally takes us to the summary of the chapter 3. We went through the basic functionalities of transport layer protocols, multiplexing, demultiplexing, reliable data transfer, flow control, and just now, congestion control. And we talk about how UDP and TCP implement these services. Particularly, we spend quite a lot of time here, as well as here. We are now finally ready to leave the network edge. So departing from the transport layer and down to the network layer and into the network core. But the network layer is going to be split into 2 chapters. Chapter 4 is going to be about the data plane, how we forward packets real fast. And chapter 5 is going to be the data plane. So how do we control these paths we select such that the packet will travel and eventually reaching the destination, reaching the receiver. All right, so that was the last bit of TCP ECN. By the way, the bit patterns that the router turned on to generate the ECN bits being sent, that pattern is not exactly what I was showing on the slide according to the spec. But somehow when this set of slides that I received from the publisher, well, it shows this way. So I'm just sticking to it. But you know that according to the spec, the exact bit patterns can be quite different. But you get the idea. Okay, so the router turns on a certain bit, and therefore when this packet is received at the receiver sends something back with special flags on. Good. Next will be chapter 4. And you heard in the summary of chapter 3 and the kind of overview, preview of chapter 4, there are 2 planes, data plane and control plane. Sorry that sometimes I would say one thing, but I meant another. Okay, so chapter 4 is data plane. Okay, you know what? It's already 12:06, so we don't have time for the overview video, which is a little bit longer than 4 minutes. So we'll actually start next week, next Tuesday, brand new from chapter 4. Okay, now to sum up for today, I would say this. Okay, go to quiz 28. I know some of you guys are probably totally confused, okay? But you know what? I think in the end, we come to the right solution. So many thanks to David, Brian, and Doris. Thank you for asking all these questions. We take more time working on this quiz, but you know what? The good thing is that it's now very clear for those who participated in the brainstorming to come up with the final answer. Okay, and yeah, Polly actually are a little bit rusty about fast recovery's finite state machine. I totally neglected the 3 duplicate ACK. There's a blue line, right? Retransmit the packet that is missing. Okay, good. So I think you guys, managed to correct accordingly. Okay, some of you might still need to correct the C. Okay, but essentially H and I, not H no packet, but I sending packet 11. Okay, C should be retransmitting the missing packet. All right, good. So that's all for today, and with that, I say goodbye. I see you next week. Oh, next week is also the midterm week. Okay, take things easy. The scope is 2.6 multimedia and chapter 3. Yeah, goodbye. Bye, Ethan. Bye, Kevin. Bye.